Everyone, welcome to the channel. So in this video I'm going to show you correcting geometric distortions using mapping functions and control points. So now let's get started. So this video introduces a very powerful and common method for correcting errors in geometry. As noted earlier, the technique also allows us to register one image to another image or an image to a map. In fact, by doing this registration, any errors are removed entirely. It is an alternative technique to the mathematical modeling approach of the previous video, and it is based upon two principal requirements. First, we assume we have available a map of the region which is corrected geometrically and is in scale not too different from that of an image we wish to correct. Secondly, we need to be able to identify the points called control points in both the map and the image so that we can tie two together mathematically. The real power of this technique lies in setting up the mathematical equations that links the points in the image with the corresponding points in the map. We will use the control points to set up those mathematical equations. In a sense, we are assuming that if we can relate the control points from the image and the map mathematically, and that control points are indicative of the map and the image geometries, then the other points in the map image will also be related by those same equations. This slide shows what we have in mind. The geometrically correct map is on the left hand side of this slide here, and the image to be corrected is on the right hand side. So you can notice that these are in opposite positions from the treatment of the previous lecture. It is just more convenient in this analysis to have them in this new order. So as before, we have chosen the coordinates of x and y to describe the position of the points or a pixel in the map, and the coordinates u and v to describe the position in the image. So in principle, it should be possible to set up equation that relate the coordinates of a point in the image, knowing its position in the map. This is shown here by a pair of functions in which the both of the image coordinates are shown as a function of both map coordinates. Those functions will contain unknown coefficient which, when given explicit values, will allow us to go between the map and the image. To find those explicit values, we need some points in common, that is simultaneous sets of x, y and u, and v that we can substitute into the equations. Those points are called the control points, or sometimes they are called as ground control points. So here we show the relationship between the points in the map and the corresponding points in the image by drawing a grid or pixel centers in each case. So what we are going to do is to choose a grid of grid position on the map, and by using the mapping functions find the corresponding grid position in the image. So what sort of functions should we use for this? Well, the simplest are the polynomials. So here we show the mapping functions expressed as a polynomials. So you can able to see this. So we have expressed our mapping function as a polynomials. In this case for order or the degree 2, in principle any order could be used, expecting that a higher order will give more accurate result. However, a higher order polynomials introduce their own problems, as we will see later. The unknown coefficients to be found using the control points are the a sub zeros and the b sub zero. If we assume that we have used the control points and identified the unknown coefficients, then we use the two mapping polynomials in the following manner. We moved over the map grid point by point, that is grid intersection by grid intersection, and for each point use the mapping polynomials to find the corresponding points in the image. We find the pixel value at that image point and transfer it onto the map position we started with. That is done for all grid positions on the map, thereby building up a geometrically correct image. Essentially using the recorded image as a source of pixels. So this slide here shows the process broken into two individual steps. At the top we find the pixel locations in the image, which corresponds to the pixel positions on the map. So the bottom we transfer the pixel from the image onto the map grid. This is just a small point, but it is worth noting the pixel that are centered on an image grid. The map or the record image are of such a size that adjacent pixels join up against each other. So there are now two important matters to be considered before the method is workable. The first is to how to determine the unknown coefficients in the mapping polynomials. And I said earlier that involves the use of control points. The second practical matter is that the mapping from a map grid position using the polynomials may not project exactly onto a pixel position in the image grid. That will form the focus of our next video. Remember that the control points are a pair of coordinates in the map and the image. Essentially, each control point is represented by a set of values of x, y, u and v. So you can able to see from this image here. So which is represented by a set of coordinates of x and y and u and v. So for example, if we had say 20 control points, we could have 20 sets of those four numbers. So what we do is substitute those knowing values into the mapping polynomials, and thus set up a set of simultaneous equations which when solved yield the required values of unknown coefficients. Clearly we need to have at least as many control points as there are unknown coefficients in one of the mapping polynomials. We can use the same set of control points to generate the unknown coefficients in other mapping polynomials. We do not need the same percent. For a second order mapping polynomials, a minimum of 6 control points is required. 3 are needed for the first order collinear mapping polynomials, and 10 are required if third order mapping polynomials are used. Usually we choose more control points than the necessary and generate at least a square estimates. So generate at least square estimates of unknown coefficients. A particular advantage in choosing greater than the minimum number of control points is that any specific control points which may not be well placed in either map or the image will not have an undue influence on the values of the coefficients being generated. Effectively, this technique depends upon having an accurate way. This technique depends upon having an accurate way of relating points in a map to corresponding points in an image. We do this by the process of choosing a control points and establishing a mapping polynomials. We will see an example in our later videos. So in this video, I have shown you correcting geometric distortion using mapping function and control points. So thanks for watching, and please subscribe to our channel and give us a like.